Fluids and electrolytes. Fluid transport and tonicity. Movement of particles across a membrane. Cell membranes are semi-permeable. They allow some things to cross and bar others from crossing. Diffusion across the membrane is influenced by the size of the particle and the size of the membrane pore. Quite often, if something is too big for the membrane pore, it's just not going to make it. Active transport. Sodium is primarily an ion within the extracellular fluid. Potassium is primarily an intracellular ion. What prevents them from evening out their concentrations? What is it that prevents this concentration gradient to remain? Well, the answer is active transport. There's a sodium-potassium pump, sometimes called the sodium-potassium ATPase pump. The bottom line is, using energy, ATP, sodium is constantly being pumped to one side and potassium to the other side. Movement of fluid across a membrane. Fluid shifting. We're going to break this conversation into two halves. One is discussing osmotic pressure, the other one's talking about hydrostatic pressure. Well, on the osmotic pressure side, we have that fluid moves in response to solutes. And these solutes are primarily plasma proteins, sometimes called colloids, or electrolytes, especially sodium. So the fluid is going to move to try and even out the concentration of these particles. Hydrostatic pressure, fluids are moving in response to the fluids. If there's too much fluid on one side compared to the other, it's going to shift across. So it's looking at the concentration of the water, not the concentration of the solute. Hydrostatic pressure makes fluids move from the dilute side to the concentrated side. Osmotic pressure, fluids move to even out the concentration of the solutes. Hydrostatic pressure, fluids move to even out the concentration of the fluids. With osmotic pressure, fluid is pulled to the area of greatest solute concentration. Fluid is pulled to the area that's the most salty, or the area that has the most plasma proteins. Hydrostatic pressure, fluid is pushed into the area of greatest fluid concentration, i.e. most dilute. With hydrostatic pressure, fluid is pushed into the area of least fluid concentration. Sometimes we refer to this as the most concentrated area. Fluid is being pushed into the saltiest area. Osmotic pressure. We talk about capillary osmotic pressure and tissue osmotic pressure. Similarly, we talk about capillary hydrostatic pressure and tissue hydrostatic pressure. If the osmotic pressure in the capillaries is greater than that in the tissues, there are more solutes in the capillaries, so fluid is pulled into the capillaries. If the hydrostatic pressure in the capillaries is greater than that in the tissue, the fluid in the capillaries is more dilute, so fluids are pushed into the tissues. Okay, let's look at this another way. The image on the left, more solutes and less water per liter. The image on the right, there are less solutes and more water per liter. So typically speaking, the box on the left is more concentrated. Osmotic pressure pulls the water towards the area of high solute concentration. Hydrostatic pressure pushes the water out of the dilute area and into the concentrated area. The body wants homeostasis. The body wants to even out the concentrations. If fluid gets shifted, the compartment is going to be much fuller. The compartment either needs to get bigger or the pressure in it is going to increase. Think hypertension here. The result is homeostasis. We have two compartments with the same concentration. This is very simplistic. As you're starting to realize, this is actually a very complex operation that's going on with many different forces pulling and pushing fluids back and forth. Okay, let's look at the solutes. Plasma proteins, colloids, are primarily inside the blood vessels. They tend to be stable unless there's an increase in vascular permeability, and then the colloids leak out. Now the electrolytes, that's your sodium and your potassium and your chloride and all that, but especially let's talk about sodium, tends to move back and forth between compartments relatively easy. It moves between the intra and extravascular spaces. All right, osmotic and hydrostatic pressure, plasma protein colloids, they tend to increase the osmotic pressure in the plasma and pull fluid into the vessels. Since there are always more colloids inside the vessel than outside of them, why don't the vessels keep filling with fluids and eventually burst? Well, we have increased fluids in the vessels. That means increased hydrostatic pressure, and that's pushing fluid back out of the vessels. When we put both of these arms together, you have homeostasis. All right, this is a diagram of showing you how intertwined the blood systems and lymph systems are. Please remember this diagram for one of our later classes. We're going to talk about the blood vessels here, but keep in mind a lot of these processes are really taking place in the lymph system as well. Okay, pushing and pulling. The blood flow in this vessel is starting at the top, moving down towards the bottom. So the top is the arterial end, and the bottom is the venous end. We see osmotic pressure is pulling fluids into the vessel, and hydrostatic pressure is pushing it out. But let's break it down to what's happening on the arterial end versus the venous end. On the arterial end, there's a lot more fluid. It's pushing stuff out. It's pushing, the hydrostatic pressure is pushing fluid out more than stuff is getting pulled in. So that the fluids can get to the tissues. The osmotic pressure at the bottom, the venous end, is pulling those fluids back in. So if this is balanced, you're not getting edema. The hydrostatic pressure at the arterial end pushes the fluid out. The osmotic pressure at the venous end pulls those fluids right back in. So again, if it's balanced, you're not getting edema.